Hey everyone, this is the second screencast in our series on Chapter 2, Section 1, the textbook. So we're looking at how to make numerical and graphical summaries for numerical variables. We did graphical summaries last time, looked at making histograms and density plots. Now we'll look at numerical summaries for a numerical variable. So these tend to be output to the console that give you like numbers and little tables. So remember that question we had about a typical fastest speed ever driven by students at Georgetown College. The histogram and the density plot we looked at suggested that if you had to answer that question, you might say something around 100 or 105 or so miles per hour. If you had to give one number, is there a way to use all the data to get that one typical number without having to kind of just guesstimate from a graph? So that's what we're going to be addressing in this part of the chapter. One possible candidate for a typical value for a list of numbers is the mean of that list of numbers. Now, the mean is symbolized X with a bar over it. X is kind of short for the data values, and the bar is like smoothing out all the variation in the data, big values, medium values, low values, smoothing that all out into one number. And it has a formula. The sample mean, the mean of the sample data, is just the sum of the data, which is this stuff on the top, divided by how many items there were in the data in the first place. And that's designated by this number n on the bottom. A lower n is usually used to indicate the size of the sample. So it's the sum of all the 71 speeds, one speed for each student in the data set, divided by the 71. Symbolically over here, the sum is represented as x1 plus x2 plus x3 plus x4. The dots say go all the way up to plus xn, x71 this time, the last of the speeds. So x with the subscript like that is each individual speed, and you're adding them all up. So you're not ever going to have to do that by hand. You can always, when you have the data in R, just make R do that math for you. And one way to do it is with the function mean. And like any function, when you use it, you start with an open parenthesis and you close with a closing parenthesis, and you have inputs. And you separate those inputs with a comma. It's not important that all of these things be on separate lines like I have it in the code. That's just easy. It makes it easier for us to read and talk about here. But those commas and those parentheses are important. And the basic usage is very similar to making a histogram or density plot. You indicate what variable you plan to take the mean of. You indicate that it is a variable with the Quartals here. And then the second input is what data set that variable lives inside of. So we're supposed to get an answer of 105.9 when we take the mean. Let's just verify that. Copy into RStudio, paste in, give it a try, and sure enough, 105.9. So you could say that the typical student drove around 105.9 miles per hour. Okay, that's what's going on typically. But of course, people aren't driving that exact speed. They're typically driving 105.9 miles per hour, give or take some. There's some variation in the speeds. But give or take how much? What's a good give or take figure to tell people if they ask you for something like that. And there's a couple of different approaches to this, but one very common approach is to give people the standard deviation of the data. Now, the standard deviation, you'll often see that written in the slides as SD for short. You'll often see it written in stats textbooks as S, sample standard deviation. It has a kind of a complex formula. Here it is. But you don't have to memorize it. And that's because R is going to compute this number for you. We'll come back to the formula, though. It is worth understanding how it works, but just rest assured you don't have to memorize it. You're just going to make R find it, and you use a function called SD. And it works exactly like the mean function and the GF histogram, the GF density work. You just say your variable, comma, the data set where that variable lives in. And so I encourage you to give that a try over in RStudio, but you can see here that what comes out is 20.8 miles per hour, 20.87, which I guess rounds up to 20.9. And so you could say that the typical student drives about 105.9 miles per hour, give or take 20.9 miles per hour or so. And that's a really good practice. Whenever you've got data that you've computed the mean and the standard deviation of, say that little sentence to yourself. Typically, it was the mean, fill it in. Give or take the standard deviation, fill it in, or so. But I want to revisit the formula a little bit to just show you why the formula makes sense as a way to be a give or take figure. And to do that, why don't we try just a small example? How about a very small data set, kind of a fake data set, consisting of just those 5 numbers, 2, 3, 5, 8, and 12. Let's compute the standard deviation for the data set one step at a time. So to get an idea of what the steps are, we should look back at the complex formula. Okay, here it is. And you see that there's a fraction here. Oops, there's a fraction bar. And on the top is a sum of some squares of things. And what are those things? x1 minus x bar, x2 minus x bar, and so on. So the x bar, that's the sample mean, that's involved in getting the standard deviation. So we're going to need to get the mean of the data first. And then apparently what we're doing is taking the first data value, x1, and subtracting off the sample mean from it. And we're taking the second data value and subtracting off the sample mean from it, all the way up to the nth data value and subtracting the sample mean off from it. And then we're adding those all together, and then we're dividing by almost how many data values there were, one less than the number of data values there were. And then at the very end, we're taking the square root of that fraction. So we just need to create that process in a series of steps. So once we got the sample mean, which I guess you could call kind of step 0 if you like, then you could proceed. Now we need the sample mean. Tell you what, I'll go ahead and get that for us here over in RStudio, because I forgot to stick it in the slides here. I will stick it in so that when you're actually looking at the slides yourself, you'll see it done. 2, 3, 5, 8, and 12. All right, oops, I want to show you this RStudio. So I'm going to get the mean of that. So I guess I'll do 2 plus 3 plus 5 plus 8 plus 12, close parentheses, divide by the 5 It's the number of items that there are there. And I get 6. Yeah, because the top added to 30 and then divide by 5, you get 6. Okay. And so then once you've got that base step going, you can subtract that mean of 6 from each of the data values. So the data values are in this column here, 2, 3, 5, x, 2, 3, 5, 8, and 12. It's this column called x. Now, if you subtract 6 from each of those numbers, you're going to get a -4, -3, a -1, a 2, and a 6. And that's how far off the data value was from the mean, how much it deviated from the mean. So these numbers here are called the deviations from the mean. Now, in the formula, it said you had to square these deviations. Remember? See the little squares here? So we're going to need to do that ourselves in the next step. So squaring the -4 deviation, you get 16. Squaring the -3, you get a 9. Squaring the -1 deviation that comes from the data value 5, you get a 1. The data value 8 was 2 above the mean of 6. Square that, you get a 4. And the last data value of 12 was 6 above the mean. Square that, you get a 36. Take these squared deviations. And the formula said you had to add them all up. So we'll do that. We're going to add them all up. 16 plus 9 plus 1 plus 4 plus 36 here along the top. And almost averaged it by dividing by 1 less than the number that there was in the data. So 1 less than 5. So 66 divided by 4. Now that turns out to be 16.5. Now that number, this almost average, is called the variance of the data. It's not a number that we've worked with a whole lot directly in an elementary stats class, but it's actually pretty important in statistics. We go one more step. The last step is to take the square root of the variance, the square root of 16.5, and you get 4.06. That's the standard deviation. So R is going through that process in order to compute the standard deviation whenever you call up that SD function on a variable in some data. So I want to take this a little further and show you how the mean and the standard deviation work together in typical data sets. Let's go back to these values here, 2, 3, 5, 8, and 12, the original data. And I'd like you to think about the mean minus the standard deviation. So that's 6 minus that 4.06. So that's about 1.94. And then the mean plus the standard deviation. 6 plus 4.06 gives you 10.06. So we've subtracted and added standard deviation to the mean. And just look at the range here from 1.94 to 10.06 and ask ourselves, how many of the original data fall inside that range? Well, the 2 does, because it's a little bigger than the 1.94. So does the 3, so does the 5, so does the 8. The only one that doesn't lie in that range is the 12. So 4 of the 5 data values, 4 out of 5, 80% of the data values fell inside that range. A majority of the data lay within 1 standard deviation of the mean. You're going to find that that happens a lot with data sets. In fact, there's a rough rule of thumb that you can use and that I'm going to ask you to always keep in mind. For a lot of data sets, about 2/3 of the data will lie within 1 standard deviation of the mean. And most of the data, about 95%, will lie within 2 standard deviations of the mean. So that's why this standard deviation is such a great give or take figure, because the typical value is going to be approximately the mean, give or take a standard deviation or so. It's going to be kind of unusual to see a data value that's more than 2 standard deviations above the mean. Kind of unusual to see a data value that's more than 2 standard deviations below the mean. So the mean as a measure of typical value, and the standard deviation as a measure of how spread out the data is. But there's other approaches. Another approach to a typical value for a data set is the median. And how do you find the median of data? Well, what you do is you just sort your data from the smallest to the largest number. So here's our small data set here, from the 2 all the way up to the 12. And then you find the data value that's closest to the middle. So that would be the 5 here. That's exactly in the middle. And when there's an odd number of data values, that's going to be the case. There will be an exact middle value. And that exact middle value is called the median. Now, how should you think about the median? Well, about half the values are below the median, and about half are above. And that's why the name median is given. It kind of sounds like middle. The median is 50% of the way through the data. I should let you know what it would be like if you had to compute the median when there was an even number of data values. And so let's imagine that over back here in oops, wrong place. Back in R, what if your data values were 2, 3, 5, 8, 12, and 14? That's 6 values. Then there's 2 values, the 5 and the 8, that are closest to the middle. And what you would do is you would average those 2 values. And so you would do 5 plus 8 divided by 2. 5 plus 8 is 13, divided by 2 is 6.5. And you would report that as the median. So you don't have to worry about those kinds of things, because you'll be asking for medians of variables that live inside a big data set. R will take care of all of that for you. Similar to medians are quartiles. The first quartile of data is going to be the number that's closest to 25% of the way through the data, instead of 50% like the median. And the third quartile is 75% of the way through the data. So if you think about it, between the first and the third quartiles, 25%, 75%, that's a 50% difference, is half. About 50% of the data values are between the first and the third quartile. So you can get the median and the first quartile and the third quartile and the mean and the standard deviation all at once if you like, with a function called FavStats. And it works exactly the way all of our other functions have worked. Twiddles the variable you want, comma, data equals the data set where the variable lives. So let's give this a try over in RStudio. And there we go. So we've got the minimum speed that anybody drove was 60 miles an hour. 25% of the people in our data set drove less than 90.5 miles per hour. 50% drove less than 100.2 miles per hour. 75% drove less than 119.5 miles per hour. The fastest anybody drove was 190 miles per hour. You know, those five numbers there, the minimum, the first quartile, the median, the third quartile, and the maximum, are often called the five-number summary for a data set. They also gave the mean and the standard deviation, how many people were involved in computing those numbers, and did anybody not report their fastest speed. There's a zero there, so there was no data missing. It was actually 71 numbers all the way through. The standard deviation is a measure of how spread out the data are. Another approach to the spread is just to subtract the first quartile from the third quartile. The result is called the inter-quartile range, or IQR for short. And so if we're looking back in our studio, if we wanted to find the inter-quartile range, we could take the third quartile, 119.5, subtract off the first quartile, and I'll try it down here like with a calculator, 119.5 minus 90.5, 29. But another possibility is, like if we didn't have the first and the third quartile staring us in the face, we could just ask for IQR, parenthesis, twiddles fastest, comma, data equals M111 survey. It's always a good idea to try things out in our studio, and copying and pasting is certainly a fine way, but it's also good to makes you more familiar with our code if you try to do it just by typing and just from memory, just to see how that will work for you. Let's give that a try here to model the process. Heading back to our studio, IQR. Oh, there it is in code completion, little IQR. I'll press enter to grab it. It gives me the parentheses. Twiddles fastest, data equals M111 survey. Oh, and that popped up in code completion, so I'll press enter so that I can have it spelled just right and then run it. When you type like that, all kinds of things can happen. Like maybe you'll accidentally misspell a variable, like maybe you'll have a capital F for fastest. Data equals M111 survey. And when you run it, you'll get an error. It'll say object fastest not found. And you'll look at it and you'll say, oh, it's not finding the variable fastest with a capital F. And then you'll head back up to your M111 survey and look inside it and say to yourself, oh, it's because the variable is spelled all lowercase. So those error messages can be quite helpful. So that's enough here for this particular screencast. We have looked at two approaches to computing the typical value for a data set, and that's the mean and the median. And we've looked at two approaches for computing spread in a data set, and that's the standard deviation and the inter-quartile range. Next time we get together, we want to talk about the shape of a numerical distribution and also another graphical device for studying numerical data that incorporates some of the numerical summaries that we've just learned about. So see you soon.